So the last thing that we're going to talk about in our section on thermodynamics is the laws of thermodynamics. So we already talked about the 0th law of thermodynamics, right? That's the one that allows us to define what temperature is. Our first law of thermodynamics basically just tells us that energy of an isolated system can never be created or destroyed. It can only be transformed. And it also tells us that the change in total energy of a system has to be equal to heat plus the work. So whenever we're thinking about thermodynamic processes, a thermodynamic process is a method by which a system is changed from one state into another state. And the state of this system is described by a set of state variables. Things like pressure, temperature, volume, number of moles, and internal energy, Gibbs free energy, and entropy. So state variables describe the state of a system at some instant in time, but these state variables do not tell us how the system got to that state. So for example, you can see here that heat, Q, and work, W, are not state variables. They describe how a system gets from one state into another state. So if a system is changed so that it is always very near equilibrium, the changes in state can be represented by a curve on a plot of pressure versus volume, right? This is just a PV diagram. And at each point on the curve, we can say that the system is in an equilibrium state. The area under this curve is going to be the work done on the system. So whenever we're thinking about work in thermodynamics, we usually define work as the work done on the gas as opposed to the work done by the gas. So this is because it makes the concept of work in thermodynamics consistent with the concept of work in mechanics. So in mechanics, the system is some object. When positive work is done on that object, the energy of the object increases. Well, when work is done on a gas, and when this value is positive, the internal energy of the gas is going to increase. So this maintains consistency between the thermodynamic definition of work and the mechanics definition of work. So we can derive an equation for work done in thermodynamics by starting with our work equation that we used in mechanics, right? Work is equal to the force parallel times our change in position. And we also know that pressure is equal to force divided by area. So I can just arrange this, and the force that is contained within that pressure equation is my force that I will plug in to the work equation. So this tells us that work is equal to pressure times area times a change in x value. So if we take an area and we multiply it by some length, right, we get volume. Well, if I take area and I multiply it times a change in length, I get volume. So the work done by the gas is equal to pressure times volume. The work done on the gas is going to be the negative of that. So an example of work done with a gas would be like a gas is being compressed in a container. So the work done on the gas is going to be positive, right? There is something compressing this gas, so the work done on the gas is positive, and the volume of the environment outside of our gas container is going to be getting larger. The work done by the gas is going to be negative, and the volume of my gas is getting smaller. If a gas is expanding, is going to be the opposite. So work done on a gas is going to be negative because this gas is pushing out towards the environment. So the environment's volume is getting smaller. Work done by the gas will be positive because the volume of the gas is getting larger. So the internal energy of a system is a state variable, and its value depends only on the current state of my system. This is an example of where the path to get there doesn't matter, right? We've talked about examples of like conservative versus non-conservative forces. Conservative forces are path independent. Non-conservative forces like friction are path dependent. So the internal energy is path independent, right? It doesn't matter what path that the system took to get from one state to another state. It only matters that it did this. So this idea of path independence brings us to the idea and discussion on reversible and irreversible processes. So, spontaneous heat flows from a hot body to a cold body, and this is always irreversible, right? So if I take a bunch of sodas that are warm and I put ice up next to them, the heat is going to transfer from my can of soda into the ice cubes, and the ice cubes are going to start to melt. We do not have this reverse heat flow spontaneously occurring. We do not have heat flowing from the ice cubes to the soda pops. So, a reversible process is one that does not violate any laws of physics if I play it in reverse, right? If I put it on rewind, it will not violate any laws of physics. So, if friction or air resistance are present, my process is irreversible, right? Because those are path-dependent processes. If I play it backwards, it would be easy to tell that something is wrong, right? So, if I imagine a block on a frozen lake, and pretend you don't see me push this block, right? You just see a block sliding from left to right over a frozen lake. Looks normal. If I play it in reverse, right, and my block is going to look like it's moving from right to left, and it's not going to look odd, right? It's going to seem like it's sliding normally, either way. The opposite of that would be like if there's a block moving across the carpet, right? If I push a block, remember, you don't see me push it. You just see like, oh, it's in motion. If a block is sliding across the carpet, it is going to have a larger velocity at the beginning and a smaller velocity at the end, right? It's going to be slowing down. If I were to play that in reverse, I would have a smaller velocity at the beginning and a larger velocity at the end. It would look like as this block is sliding across the carpet, it is speeding up, right? It would be very easy to tell that something is wrong. We may not know exactly what is wrong, but we would look at this and say, that's not like what my life experience is like. I have never seen something slide across a carpet and speed up. So, that is an irreversible process. The block's sliding across the carpet. And this is because the process of energy dissipating throughout this motion, it always makes a process irreversible. Like sliding friction, air resistance, these always make a process irreversible. And that is because we are losing energy from the system in the form of heat. Specifically with friction, we are losing energy from the system in the form of heat. And we cannot get that heat back, transform it back into some sort of kinetic energy. So, also, a system is never going to spontaneously go from a disordered state to a more ordered state. Meaning, your house is never going to go from dusty to no dusty unless you put work in and you dust your house, but your house will always go from impeccably clean to dusty without you putting in any work. So, reversible processes are those that do not change the total amount of disorder in the universe. An irreversible process increases the amount of disorder. And this leads us to our second law of thermodynamics. And the second law of thermodynamics tells us that the total entropy of an isolated system can never decrease over time. It is either going to increase or remain constant. And that's because natural processes, right, if there's no external influence, no external factors, natural processes always tend to move towards a state of maximum entropy or maximum randomness. Oftentimes, we use entropy and disorder interchangeably, but that's not actually like a great parallel. Entropy and randomness is a much better parallel. So, this law introduces the concept of irreversibility and explains phenomena like heat flowing from hot to cold spontaneously. So, the entropy of the universe is never going to decrease, meaning the randomness of the universe is never going to decrease. It will either remain the same or increase. A reversible process causes no change in the total entropy of the universe. So, entropy is a fundamental concept that connects the microscopic behavior of particles to their macroscopic properties. Entropy is a measure of the number of microscopic configurations or arrangements of particles and energy states that correspond to a macroscopic state, right? Like an overall observable property like temperature and pressure. So we can think about this, like how many different ways can I position my atoms and how many different velocities can my atoms have inside of a container that will produce the same temperature and pressure, right? There's a variety of different configurations. How many are there? And that tells me what the entropy of my system is. So in statistical mechanics, entropy is related to the probability of different microscopic states occurring within a system. It quantifies the degree of uncertainty or randomness in the distribution of particles or energy states. Uncertainty or randomness, not disorder. So, this is a great example. So, we have 4 particles and a box with 2 different containers. So, we have one macroscopic state in line A, right? And there's only one microstate to get this macroscopic state. Meaning, in order to get a state that has 4 balls in the left box, this is the only way to do it. The organization within this box doesn't matter right now. The colors are for later. So let's say that we want to have a state that has 3 balls in the left box and 1 ball in the right box. Well, we have 4 different variations to create this macroscopic state, meaning that there are 4 microstates. 4 microstates. So we could have green, yellow, and blue on the left, and red on the right. We could have red, blue, and yellow on the left, and green on the right, and so forth, right? There are 4 different ways that we can create a configuration that has 3 balls in box 1 and 1 ball in box 2. Now, what if we want 2 balls in box 1 and 2 balls in box 2? Well, there are now 6 different ways, or 6 different configurations that we can have to produce this macroscopic state. This one, with 6 microstates, has the largest entropy. And so, in statistical mechanics, the behavior of a substance is described by the statistical behavior of the atoms and molecules contained in it. And one of the main conclusions of the statistical mechanical approach is that systems tend towards greater disorder or greater randomness, and entropy is a measure of that. So entropy is our letter S, and it is equal to the Boltzmann constant times the natural log of W. So W, in this case, is a number that is proportional to the probability that a system is in a specific configuration. It's something called a weighting function. It's the number of microstates, right? So my W is what's happening in this right-hand column, my number of microstates. So here is a plot of that, right? As my number of microstates increases, my entropy also increases. So let's say we have an ideal gas. Microscopically, we have individual gas molecules moving randomly, colliding elastically with each other, and also the container walls. Macroscopically, the entropy of an ideal gas increases as the volume or temperature increases, and this reflects the greater number of microstates that are accessible to the gas particles. So the connection here is that the Boltzmann formula links entropy to that number of microstates, demonstrating that increased molecular randomness, or increased molecular disorder, as some people say, corresponds to a higher entropy. So, like I said, as we increase our number of microstates, our microstates is going to be this, the x value. As we increase our number of microstates, we increase our y value, or our entropy of the system. And entropy in the universe, I think, are really fascinating, because if we think about this, right, the entropy of the universe is never going to decrease. It is always going to remain the same or increase. And also, a random arrangement is much more probable than an orderly one, if we just allow the laws of nature to carry out without influence. So, you are more likely, if I have a deck of cards, and I shuffle this deck of cards, and I hand everybody 5 cards, you are more likely to get this hand on the right than you are to get the one on the left. Now, is it possible to get the one on the left? Yes, it is 100% possible. But as far as probabilities, you are much more likely to get this disordered state on the right-hand side than you are for me to shuffle the cards, randomly dish out some cards, and you look at your deck and you say, oh my gosh, this is a perfectly ordered set of the face cards of diamonds. There's a name for that. I don't know what it is. And it doesn't matter right now. So, entropy of the universe increases in all natural processes, right? And although the entropy of the universe always increases, we can decrease the entropy within a system. So examples of that, right? On the left-hand side, we are going to see reducing entropy in the system. Sorry, that's the left. On the left-hand side, we're going to see reducing entropy in the system and increasing entropy elsewhere, right? Because we have to have a balance. If we decrease it somewhere, it increases somewhere else. So a refrigerator is a great example of that. So in a refrigerator, heat is removed from the interior and decreases the entropy of the refrigerator system. The problem is that if you go stand by your refrigerator, it is going to be noticeably warmer than the rest of the kitchen, especially down by the bottom, right? And this is because the refrigerator dumps heat into the environment, increasing the entropy of the surrounding air. Another example is during the formation of crystals, or when particles arrange themselves in an orderly state, crystallization, right? We are lowering the system's entropy. It is becoming much more, there is less randomness. The location of an atom is much more predictable in a crystallized or solidified state. And during this process, energy is released, increasing the entropy of the surrounding system, right? Heat is transferred to the surroundings. Another great example would be the assembly of nucleotides into like a DNA strand, right? We have taken something that is very random and organized it into a predictable structure. We had decreased that entropy of the system, but this requires a massive amount of energy, and where breakdown of ATP increases, entropy in the surroundings of the system, right? So we can decrease or reduce entropy in a system, but that results in an increase in entropy elsewhere. So we can kind of think of entropy as like a soup, right? A low entropy soup means it's not all mixed together. If I want to make a vegetable soup and I have carrots and celery and what else goes in vegetable soup? Potatoes, right? A low entropy soup would mean that I have one layer of carrots, then a layer of celery, then a layer of potatoes, then somehow magically all of my broth is sitting on top. And this is low entropy because if I were to come back to my soup later, because nothing is mixed together, I would be able to say, I know exactly where the carrots are. I know exactly where it is. There is no uncertainty there. There's no randomness. It's very predictable. A high entropy soup would be the soup that we want to eat, right? Everything is evenly distributed. There's a huge number of different ways that my carrots and potatoes and broth and celery can all be mixed together. And if it's sitting there, there is a probability that I say, okay, I made this soup. I see that there is a carrot sitting on the top right corner at like 11 o'clock in my pot. If I come back 6 hours later, that carrot may not be there anymore. It's going to be somewhere else. And there's a variety of different microscopic arrangements of all of my vegetables that can end up in a macroscopic state of soup. So, entropy is not really about disorder. It's about randomness. So if I dissolve a bunch of sugar in water, that sugar water looks super ordered, right? Like there's an even distribution of sugar throughout my water, but it's a high entropy system because there are thousands of different arrangements of the sugar water molecules that can create this macroscopic sugar water state. And that's why I think that clarifying that it is more about randomness and possibility of different arrangements more so than it is about disorder, because disorder is something that we generally rely on like visual interpretation to note that something is disordered versus ordered. And I think that sugar water, that's a great example. I came up with a good example. Sometimes my PowerPoints are a surprise to me, and I forgot I came up with that, and that was good. So, if we want to calculate the change in entropy during a transition between two states, we need to find a reversible path that connects those two states together. So, we need to do this because quantities like temperature of a system can be defined only for systems in equilibrium, right? So that zeroth law of thermodynamics. And a reversible path consists of a sequence of equilibrium states where we can clearly define temperature. So, reversible path, system changes from one equilibrium state to another equilibrium state in a way that can be reversed at any point without leaving any trace of itself on the surroundings or the system itself. Irreversible path would be a system changes from one equilibrium state to another in a manner that cannot be exactly retraced if we reverse this process. So any sort of heat loss to the environment would be irreversible. So reversible path would be a very slow expansion or compression of a gas, while irreversible path, mixing two substances together, or really any process involving friction, heat transfer between the system and its surroundings. And I gave you examples of the lake already. So, you saw that PV diagram earlier, right? And it has that little curve to it. That is an example of a reversible path. An irreversible path, we have this straight line representation. So, the third law of thermodynamics tells us that as the temperature of a system approaches absolute zero, the entropy of a perfect crystal also approaches zero. Achieving absolute zero would mean achieving zero entropy, which is unattainable. That is not possible because it would require removing all thermal motion from particles and leaving them in their lowest possible energy state, and this is really difficult to achieve because any interaction with the surrounding environment or residual energy would prevent the system from achieving absolute zero. Now we can get stuff really cold, but we cannot get it to 0 Kelvin. So this is because as temperatures approach absolute zero, we are shifting from classical effects to quantum mechanical effects. The colder something gets, the more and more it tends to produce quantum mechanical effects, and those they dominate classical mechanics. So these effects are things like the Heisenberg uncertainty principle, which tells us that we cannot simultaneously know the exact position and momentum of a particle at the same time with absolute certainty. I can know the position, but my momentum is questionable. Or I can know the momentum, but my position ends up becoming questionable. I don't know exactly where it's at. And this fundamental uncertainty implies that even in the absence of external factors, particles are always going to have some residual motion or energy, and this is going to prevent them from reaching a state that is completely at rest. So, what is this residual energy? Well, this is, in an attempt to reach 0 Kelvin, according to classical physics, the kinetic energy would go to 0, and there would be no motion at all. But according to quantum theory, the electrons will always retain some amount of residual energy, and this residual energy is something called 0-point energy. And 0-point energy is what leads to the creation of instantaneous or induced dipole moments within the electron cloud of an atom, and this microscopic quantum fluctuation in the density of the electrons actually results in a macroscopic phenomenon that you all are probably familiar with. Van der Waals forces, more specifically the London dispersion force, but colloquially, Van der Waals forces, right? So the London dispersion force is actually a quantum mechanical effect coming from the random thermal motion of electrons within that electron cloud. So 0-point energy leads to electron fluctuations, which leads to temporary or induced dipoles, which produces these London dispersion forces. And if we didn't have this quantum mechanical 0-point energy, then electrons would be perfectly still at low temps. We would have no fluctuations, no temporary dipoles, and also no London dispersion forces.